Ah. All right, we are live.
So today I'm going to do Unit 4 with you, Triangle Similarity. I know you did with Mr. Woods the other day, Triangle Congruence. It's very similar. I know you just finished Transformations yesterday with Ms. Nichols. This unit is not that hard. For this one, the most important part about this unit is that you understand that similar figures keep their angles, meaning their angles are going to be congruent, and then their sides are proportional, meaning they are getting bigger or smaller by the same amount. Those two things, similar figures have congruent angles, similar figures have proportional sides. That's the most important part from Unit 4. You just leave it. And then we'll see at the end. It's okay. Now, typically when we're doing this unit, they're going to already give you that similarity statement. But since we're not there yet, we'll talk about how we pick the corresponding sides. Here they already marked them as congruent. I know A with my one arc mark must correspond to D. If these two triangles are similar, then angle A is congruent to angle D. Here I have B with my two arcs, E with my two arcs. B corresponds to angle E. And again, because they're similar, angle B is congruent to angle E. That leaves me left with C and F. They're corresponding, making them congruent. That just means if they tell me that these two triangles are similar and A is a 50-degree angle, I know D is a 50-degree angle too. I don't have to do any math. The angle measures aren't changing. Now, when we're doing corresponding sides that are proportional, to figure out the corresponding sides, it's just the letters that go together. AB must correspond to DE. AB has a length of 6, DE has a length of 3. That really means AB is twice as long as DE. That proportion there, it being twice as long, is going to be the same for every side. I know BC must go with EF. BC is 9, EF is 4.5. 9 is twice as big as 4.5. Same thing here. CA must go with FD, where CA is 10, FD is 5. CA is twice as long as FD. This part, this similarity statement, this part matters because either that's how we're picking our corresponding sides, or in a proof, that's what we're trying to prove. You can name that first triangle whatever you want. ABC, BCA, CAB. All that matters is that when you write your second triangle, the corresponding parts are in the same order. So I have ABC, that little squiggle means similar, is similar to, I know A goes with D, B goes with E, and C goes with F. So I put them in the same order. Triangle ABC is similar to triangle DEF. Again, typically they're not going to give you a figure where they mark the angles and all the sides. So we would use this similarity statement to figure out all these corresponding sides and angles. From there, you're just taking it in the same order. The first letter here corresponds to the first letter here. The second with the second, third with the third, and then again, same thing for sides. If I'm using my first and second letter, it's going to correspond to my first and second letter there. Again, the takeaway here, the angles are congruent and the sides are proportional. Here, this first example, we are trying to solve for our missing side. We want to solve for AC. To figure out sides, we know they're proportional. We're just setting up proportions. The side I need to use is AC because that's what I'm solving for. To figure out AC's corresponding side, I'm going to look at this similarity statement here. A is my second letter, C is my first. I know AC corresponds to my second and my first letter. I set it up as AC over DF. Then I'm going to set that equal to another set of corresponding sides. In this case, I'm going to choose AB because I chose AB, my second and third letter. What's AB's corresponding side? DE, good. So I'm going to set it up as AB over DE. There's my proportion. I'm going to plug in the values I know. I don't know AC. I'm going to give it a variable. I'll call it X. I know that DF is 30. I know X over 30 is equal to AB, which is 20, over DE, which is 50. There's my proportion. I set up a set of corresponding sides, and I set them equal to each other. Once I have that proportion set up, all we have to do is cross multiply. Remember, when we're saying cross multiply, we are just crisscrossing. And I'm going to do X times 50, which gives me 50X, and then 20 times 30, which is 600. I know 50X equals 600. I want to solve for X, so I need to divide both sides by 50. 50x divided by 50 is X. 600 divided by 50 is 12. I know X is 12. We plugged in X for AC. So if X is 12, the length of AC is also 12. When we set up this proportion, I had to use AC over DF because AC was what I was solving for and DF was its corresponding side. I set it equal to AB over DE. You also could have set it equal to CB over FB. You still would have gotten the same answer. What this really means to me, 12 over 30 is equal to 20 over 50. 12 over 30 simplified is 2/5. 20 over 50 simplified is 2/5. Again, all that's saying is these sides are 2/5 the length of their corresponding sides in that second triangle. They're either only going to ask you to figure out the angle or figure out the side. The angles, you don't have to do math. If the angles are corresponding, they're congruent. Here, similar sides, just setting up a ratio, setting up that proportion and cross multiplying. Questions on that one? No? All right. The next one, basically the same thing, only for this one, now we're dealing with coordinates. Now I'm going to show it to you using that same thing, doing the ratio, and then we'll talk about an easier way that you can solve this. What this is saying is I have two triangles. I have this little triangle here, SOT, and it's similar to my big triangle, UOB. If I'm doing it based off of the side lengths again, in my little triangle, I have side OS, and it corresponds to side OU. Again, I'm taking it right from that similarity statement. So I'm going to put OS over OU, and I'm going to set it equal to this side in my small triangle, which is OT, over that side in my big triangle, which is OB. There's my proportion. Now I'm just going to fill in their side lengths. I know O is at 0, 0, S is at 0, 2. That gives me a side length of 2. To go from 0, 0 to 0, 4 gives me a side length of 4. I set that equal to from 0, 0 to 3, 0, a side length of 3. And really what I'm trying to figure out is how long is that side. So I'm giving my variable there. There it is. It's set up. I got my proportion. Just like before, I'm just going to cross multiply. When I do 2 times x, I get 2x. 3 times 4 equals 12. Again, I want to get x by itself. I divide each side by 2. x is equal to 6, and we plugged in x for OV. What that really means to me is the length of this entire side is 6. So I'm going from 0, 0, I slide over 6, and I end up at 6, 0. Now, using the ratio here, setting up the proportion, that will work. But there is an easier way to solve this problem. I set it up as the proportion and cross multiplying, so you recognize that proportions are always multiplying. If something is getting bigger, we're multiplying it by a whole number. If something is getting smaller, we are multiplying it by a fraction. Again, if you know that, if you understand that proportions are being multiplied, you don't need to do this step. I just didn't want you to see it and think it's like a translation where to get from 0,2 to 0,4, we just slid up to. If you recognize it's a multiplication problem, to get from 0,2 to 0,4, I would have to multiply it by 2. 0 times 2 is 0, 2 times 2 is 4. I just repeat that rule. 3 times 2 is 6, 0 times 2 is 0. I end up at 6, 0. Again, what this really says is triangle SOT is half the size of triangle UOV, or vice versa. UOV is twice as big as SOT. Questions on that one? Again, same thing, proportion. Sides are proportional. You're just setting up the proportions and then cross multiplying. Now, everybody's favorite parts. This is a short unit, but it has proofs. I know we don't like proofs. There's no way to avoid them. You're definitely going to have at least one proof about triangle similarity on the EOC. Aside from knowing that similar figures have congruent angles and proportional sides, these 3 shortcuts are the big takeaway from this unit. You have the angle-angle similarity shortcut, you have the side-side-side similarity shortcut, and you have the side-angle-side similarity shortcut. The rules about angles and sides still stay the same. If we're talking about similar figures, we're talking about angles that are congruent and sides that are proportional. Meaning when I'm talking about angles in these shortcuts, the angles need to be congruent and the sides need to be proportional. This first one, angle, angle. I know angle A is 57 and so is D, so they're congruent. C is 78 and so is F, so they're congruent. Having 2 sets of congruent angles is enough to prove the triangles are similar. I don't need to know the third angle, and I don't need to know any of their sides measures. You've got 2 sets of congruent angles, the triangles are similar, your work is done. Side, side, side similarity. You need 1, 2, 3 sets of proportional sides. This one, you don't need to know any angles, but side, side, side only works if you know 5 out of the 6 sides of your 2 triangles. You need to know all 3 sides from one and at least 2 of the 3 sides for the other. Otherwise, I can't set up proportion to figure out if the other set of sides are proportional. The only one that may trick you up is that side angle side, because for this one, the order matters. It can't just be any 2 sides and any angle that you want. The angle has to be that included angle. What I mean there is if I have 2 triangles and they say to me, all right, this side is proportionate to this side is proportionate to this side, and then these angles are congruent, that works. Because looking at that, it falls in that same order. It's a side, then an angle, then a side. You may get triangles and they say, this is proportionate to this side is proportionate to this, and these two angles are congruent, if you get something like that, that's not going to work. You can't use the side angle side similarity theorem if it's going side side angle or angle side side. It needs to be a proportionate side, a congruent angle, a proportionate side. Meaning it just needs to fall in that same order. Again, aside from knowing that similar triangles have congruent angles and proportionate sides, you need to know this because you're definitely going to have a proof, and these are the only ways to prove that triangles are similar. Now, proofs. They are a daunting task. I understand that. Remember on the EOC, you don't lose points for putting the wrong answer in. Whether you leave it blank or you get it wrong, it doesn't count against you. You only get points for the right answer. So here, trying to make educated guesses, don't leave the proof blank. Sometimes things are common sense. You may be able to get an answer. It's better to try than to just leave it blank. It's not going to count against you. This one, the first one, we're trying to prove these two triangles are similar. My first statement is always the first bit of information that was given to us. My first reason is always that it's given. Here, what they told us was that AD equaled 6, DC equaled 3, BE was 4, and EC was 2. Again, they told us that in this little box up here, and they also gave you the figure where they labeled the parts. Now, the next one here, they're saying that side CA is equal to CD plus DA. Really what they're saying is this entire piece is equal to this piece plus this piece. Same thing on the other side. This entire side CB is equal to CE plus EB. All we're doing there is we're adding two segments together. And that is just that segment addition postulate. And again, that segment addition postulate says this piece plus this piece equals the entire thing. Here, using an educated guess, we obviously don't expect that you're going to remember every single theorem and postulate that you've learned this year. Taking a second and thinking, what did I do here? All I did here was I added this segment plus this segment to make this whole side, and then I added this segment plus this segment to add the whole thing. I get that segment addition postulate. The next step, again, I have my statement. I'm looking for my reason. Here, I'm saying I set up my proportional sides, CA over CD and CB over CE. In my big triangle, I have side CA. I know it corresponds in my little triangle to CD. From there, CA has a length of 9, CD has a length of 3. 9 divided by 3 was 3. And then same thing over here. In my big triangle, CB corresponds in my little triangle to CE, where CB is 6, CE is 2. 6 divided by 2 is 3. Here, taking an educated guess, what did we do? Well, I divided 9 by 3 to get 3, and I divided 6 by 2 to get 3. All I did there was divide. I used the property of division. There, that's not a fancy theorem or postulate. It's just, what did you do? I just divided. Not everything is as complicated as we would believe when we see a proof. Here, I know it's easy now once it's filled in to be like, oh, that's common sense. All you did was divide. Trying to take a second, make an educated guess. What did I do? 9 divided by 3 is 3. 6 divided by 2 is 3. All I did there was use division. The next step, this time they're giving us the reason, which is the transitive property, and we need to figure out the statement. The transitive property is really the substitution property. If they're asking us to use the transitive property, really what they're asking us to do is simplify this step. In this step, I know that CA over CD equals 3, and I know that CB over CE equals 3. If they both equal 3, then they must equal each other. There's just that substitution, that transitive property. We simplified the step above. If in the step above, CA over CD equaled 3 and CB over CE equaled 3, they both equal 3, then they both equal each other. Again, transitive property, it's just substitution. This is from an old EOC. If this year on the EOC, they ask you the transitive property, you're substituting. You're simplifying the step before. How can I make this simpler? Well, if they both equal 3, they both equal each other. The next part, I know this part is when it gets scary, when you have no statement and no reason. Look at this point at what you already know and then compare it to what you still need to figure out. Here, hopefully you recognize we only have one more step before we have to prove these two triangles are similar. The only way to prove triangles are similar is to prove they have two sets of congruent angles, to prove they have three sets of proportional sides, or to prove they have two sets of proportional sides and a set of congruent angles. Here, I have my two sets of proportionate sides. So I either need to prove I have a third set of proportional sides, or I need to prove that I have an included angle that's congruent. If we were going to use side, 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 remember, you've got to know 5 out of the 6 sides. I only know 4 of my sides. I can't figure out if DE is proportionate to AB because I don't know either one of those sides, which means my only option here is to use that side angle side similarity. I have a proportionate side here. I have a proportionate side here. I know my congruent angle needs to fall in between these two sides, which leaves me with the only possibility for the angle I need to prove congruent is this one. Now, that's angle C. However, both triangles are sharing that angle, so we can't just call it angle C. In my little triangle, it's angle DCE. In my big triangle, it's angle ACB. Even though they're labeled two different things, they're still this angle right here, which means they're the same angle. Anytime something is being compared to itself, angle C is congruent to angle C. Side AB is congruent to side AB. Anytime something is congruent to itself, that's that reflexive property. 100% chance you are going to have at least one proof on the EOC that's going to use the reflexive property. So remembering that one, the reflexive property. Anything that is congruent to itself is that because of that reflexive property. Then from there, we're done. We have proven the triangles are similar. Here, I only have a 1 in 3 chance. There are only 3 options here. It's either because of angle, angle, side, 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 or side, angle, side. For this particular problem, we had 2 sets of proportional sides, 1 set of congruent angles, so we use that side, angle, side similarity theorem. Which again, they're definitely going to ask you a proof where you have to prove that the triangles are similar. Your only answer there, side, 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 or angle, angle. That's why you got to make sure you remember those 3 shortcuts. Again, here, looking at it, now it doesn't seem as bad when it's all filled in. Take your time on the proofs. Not everything is a complicated theorem, postulate, something crazy. Sometimes things are exactly what you did. Here, I added segments. I got the segment addition. Here, I divided numbers. I used division. Questions on that one? Again, try not to leave it blank. Take a guess. The next one. Again, it's another proof. This time we're going to prove the triangles are similar, and then we're going to take it one step further. This time, again, my first statement was the first thing they told us. My first reason was it was given. What they told us up here was WI was parallel to SG. Again, recognizing those two lines next to each other mean parallel. They also, once again, gave you the figure where they marked with the arrows that those two sides are parallel. The next thing, they told us that WNI, which is this angle right here, is congruent to GNS. Looking at those two angles, you need to recognize anytime angles are forming that X there, they're crisscrossing. Where the top looks like a V for vertical, and the bottom looks like an A for angles. Vertical angles are always congruent. These two angles are congruent because they're vertical angles. Another one, 100% chance there is going to be a proof with vertical angles on the test. You're definitely going to see the reflexive property. You're definitely going to see vertical angles theorem. Again, X. Doesn't matter if it's upside, if it's right side up, if it's turned on its side. Anytime they're forming an X where the top looks like a V and the bottom looks like an A, vertical angles. Next one, alternate interior angles theorem. Here we need to know what alternate interior angles are. When we're saying interior, the angles themselves fall in between my parallel sides. Alternate meaning they're on opposite sides of my diagonal. If I'm using this diagonal here, IF, in between my parallel sides and then on opposite sides of my diagonal, on top of this line, I have angle I. On the bottom, I have angle S. Those two angles are alternate interior angles. I know, and hopefully you guys know, that alternate interior angles are always congruent. So I know angle I is congruent to angle S. If by chance you knew what alternate interior angles were, but you forgot what the theorem says, anytime we're talking about similar triangles, the angles are always going to be congruent. So anytime we're talking about angles, be it vertical angles, alternate interior angles, they're going to be congruent. That's what's true in similar triangles. Now, you also have the other diagonal WG. If you had used diagonal WG, on top of the diagonal, you would have had W. On the bottom, you would have had G. W and G are also alternate interior angles, meaning they're also congruent. At this point, I'm using angle-angle similarity. I need a similarity statement about my two triangles. Remember here, when you're writing this, the order matters. You can call the first one whatever you want, WNI, WIN, NWI. All that matters is when you write the second part, the corresponding parts are in the same order. This one was nice because they gave us angles and I just kept those. I just changed the angles into triangles. And I know triangle WNI is similar to triangle GNS. Again, I know W goes with G, N goes with N, and I goes with S. Now, this time, we've proven they're similar, and they want us to take it a step further. On Monday, when you did triangle congruence with Mr. Woods, or yesterday. So when you did triangle congruence with Mr. Woods, they had that nice little acronym of that CPCTC that tells us the corresponding parts of congruent triangles are congruent. We're saying the exact same thing here. Similar triangles just don't have an acronym. We know from that first side of this paper, if two triangles are similar, all of their corresponding angles are congruent and all their corresponding sides are proportional. All they're asking us here is, how do we know that their sides are proportional? I know their sides are proportional because in all similar triangles, the corresponding sides are going to be proportional. Again, that is just taking the same idea of that CPCTC and using it for similar triangles. We just don't have a nice neat acronym here. The only thing they will ask you after they ask you to prove triangles are similar, they're either going to ask you to prove another set of sides are proportional, like they did here, in which case we'd say all the corresponding sides of similar triangles are proportional, or they may ask you to prove that a set of angles are congruent. That's the only other thing they could ask. They're either going to tell you they're similar and then ask you to prove the sides are proportional, or ask you to prove the angles are congruent. If here they had said, prove angle W is congruent to angle G, we would have just said the corresponding angles of similar triangles are congruent. So again, that's true for all triangles. If two triangles are similar, their angles are congruent, their sides are proportional. That is a fact. You don't need to give a theorem or prove it. That is true. If two triangles are similar, their angles are congruent, their sides are proportional. Questions on this one? All right, the last one, another proof, only this time it's not in like the statement and reasons order. This time we are trying to prove these two triangles are similar using a series of transformations. But you haven't done yet, Ms. Nichols will teach you that tomorrow. Hopefully, in a perfect world, you recognize these two triangles are different sizes. Who knows the transformation that makes something bigger or smaller? Thank you, a dilation. Hopefully, we recognize that this is a dilation. If you don't, it's fine. We can still figure it out. To prove triangles are similar, it doesn't matter now that we're talking about transformations and it's on a coordinate plane. The rule's still the same. We either prove their angles are congruent or we prove their sides are proportional. I can't prove any of their angles without a compass. I don't have one. I'm going to work with their sides. Now, assuming you don't recognize it as a dilation, because they're both in the same orientation, they haven't turned like a rotation or flipped over like a reflection, I'm deciding between a translation and a dilation. If I want to see if it's a translation, I am going to plot my points. I know P is at -1, 4. That's going to transform to become A. And again, I take it from that similarity statement, first letter with the first letter. P was at -1, 4. It becomes A at -2, 8. Q at 1, 2 transforms to become C at 2, 4. And R at 4, 2 transforms to become B at 8, 4. Again, assuming I don't recognize it as a dilation, I'm going to start with the translation because the translation is our easiest transformation. If this is really a translation, the rule is going to repeat for every single set of coordinates. So I'm just going to look at what is the rule that got me from P to A. Well, to get from -1 at P to -2 at A, I subtracted 1. To get from 4 at P to 8 at A, I added 4. Now, if this is really a translation, that rule is going to work to get Q to C and R to B. The rule is always the same. So I check. Is 1 minus 1 2? No. 2 plus 4 is not 4. I know it's not a translation. This rule doesn't work. Now I'm going to check and see if it's a dilation. If it's a dilation, I'm going to multiply the numbers. So I'm going to say, is there a way for me to get from -1 to -2 by multiplication? Yes, I can multiply by 2. So checking that, -1 times 2 is -2. 4 times 2 is 8. My rule there was I multiplied by 2. Again, just like with transformations, if this is really a dilation, that rule is going to be the same for everything. So I check it for Q to C. 1 times 2 is 2. 2 times 2 is 4. That rule is still the same. 4 times 2 is 8. 2 times 2 is 4. That rule works there. I know that figure PQR, when I multiply it by 2, it will become triangle ACB, which just means I dilated triangle PQR by a scale factor of 2. At the end, when it's saying that you centered at the origin being 0, 0, just right here, we always, and I know I normally say don't assume in math, we always assume it's 0, 0 unless they tell us otherwise. This just tells me that triangle ACB is twice as big as triangle PQR. Now, solving it this way will work. I know I have some students who don't like coordinates. We try to avoid them at all costs. That is fine. If you don't like coordinates, we can solve it too. I use coordinates so that we could see it wasn't a translation. Again, taking a second to look at this before you try to solve it and recognizing hopefully that these two triangles are different sizes, it must be a dilation. If you didn't like coordinates, we could do it based off of their side lengths. Same thing we did when we were trying to solve the missing sides. If I took here, side CB, I know that CB is going to correspond from my thing, my second and third letter with QR. Looking at that, I just count. CB is 1, 2, 3, 4, 5, 6. And QR is 1, 2, 3. 6 divided by 3 is 2. CB is twice as long as QR. If I want to make sure that rule works for all my sides, I pick another side. I'm going to do AC. And I know AC, my first and second, must correspond to PQ. Again, I'm just counting. The length of AC is 1, 2, 3, 4. The length of PQ is 1, 2. 4 divided by 2 is 2. AC is twice as long as PQ. From there, you're getting the same answer. That's telling us the same thing. You can use the coordinates. You can just set up the proportions the way we did for the other sides. Whatever works best for you. Again, here, taking a second, looking over the picture, that can make your life easier. I recognized right off the bat they were different sizes. I knew it was going to be a translation. Nope, a dilation. And I knew it didn't turn at all. The orientation didn't change. So I knew right off the bat I wasn't looking at a reflection or a rotation. Now, that is it for this unit. Again, the key takeaways here are that in congruent or similar triangles, the angles are congruent and the sides are proportional. And then knowing those 3 shortcuts. You've got to know angle, angle, side, 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 and side, angle, side. Again, I know you had Mr. Woods. There's a lot of shortcuts for triangle congruence. For triangle similarity, just those 3. You know that those 3 shortcuts, you know that the angles are congruent and the sides are proportional, and you will be successful on this test. Any questions for me? No? Okay. Hang on to those papers for Mr. Perez. I don't know how he's going to grade them for you.
Thank you, Mrs. O'Connor. Nice job. All right, nice work.